Every single time you look up at the night sky, you're being lied to, not by anyone, not intentionally, but the universe itself is showing you a version of reality that no longer exists. Everything you see up there, every star, every speck of light, is a ghost, a message from something that may already be dead. And when scientists built the most powerful telescope in human history and finally pointed it at the edges of the universe, what they found didn't just surprise them. It broke their models. 300 galaxies that shouldn't exist. Black holes that are too big, too old, too there. And objects so strange, so unprecedented, that astronomers are still arguing about what the hell they actually are. Stay with me, because by the end of this video, you're going to see the universe completely differently. And I promise, that's not a metaphor. Let's start with something that sounds simple, but will genuinely mess with your head if you sit with it long enough. Light is the fastest thing in the universe. 300,000 kilometers per second. Nothing goes faster. Nothing can go faster. It's not a technology limitation. It's a fundamental law baked into Einstein's equations, and in over 100 years, nobody has found a single loophole. 300,000 kilometers per second sounds absurdly fast, and it is. Point a laser at the moon and the beam hits it in just over a second. 1 second. To cross nearly 400,000 kilometers of empty space. But here's the thing. Here's the thing that changes everything. That speed, as insane as it is, means that light takes time to travel. And that means when you look at something far away, you're not seeing it as it is now. You're seeing it as it was when the light left it. When you look at the moon, you're seeing it as it was 1.3 seconds ago. Fine, whatever, not a big deal. But the sun? The sun is 8 light minutes away. The sunlight hitting your face right now left the surface of the sun 8 minutes ago. If the sun just silently switched off, right now, at this exact moment, you wouldn't know. You'd sit there for 8 full minutes, completely unaware, looking up at a star that no longer exists. And it only gets weirder from there. Jupiter, 40 minutes. Saturn, over an hour. Neptune, 4 hours. And that's just our solar system, our cosmic backyard. The nearest star to us beyond the Sun is Proxima Centauri, 4.24 light-years away. The light we receive from it today left its surface 4 years and 3 months ago. We are literally looking into the past. Not as a poetic idea, not as a metaphor. Physically, actually, literally. Looking into the past. Every photon that enters your eye is a messenger from a time that no longer exists. Now, scale that up. The Andromeda Galaxy, our nearest galactic neighbor, is 2.5 million light-years away. The light we see from it tonight left those stars before humanity existed, before Homo sapiens took a single step, before our species drew a single breath. When you look at Andromeda, you are watching a world from before humans. And the most distant galaxies we can observe? Their light has been traveling for 13 billion years. We see them not as they are, but as they were when the universe was a newborn, when the very first stars were just flickering on for the first time. So what is a telescope, really? A telescope is a time machine. It's a machine that collects these ancient messengers, photons that have crossed billions of years of expanding space, and assembles them into an image. The bigger the mirror, the further back in time you can see. And the James Webb Space Telescope is the most powerful time machine humanity has ever built. Before we get to what Webb found, and trust me, you need to understand what Webb is before the discoveries hit you properly, let's talk about why building it was almost impossible. Before Webb, we had Hubble, And Hubble was extraordinary. The pillars of creation, the deep field images, thousands of galaxies packed into a patch of sky the size of a grain of sand held at arm's length. Hubble gave us the most iconic images in the history of astronomy and completely transformed our understanding of the cosmos. But Hubble had a blind spot. Hubble saw primarily invisible light, the same wavelengths our eyes detect. And for nearby objects, that's perfect. But for the ancient universe, the universe from billions of years ago, visible light is useless. Here's why. The universe is expanding. It's been expanding since the Big Bang, and as it expands, it stretches everything inside it, including light. A photon emitted 13 billion years ago as visible light has been traveling through a universe that never stopped growing. As space expanded, it literally stretched that photon's wavelength longer and longer and longer, until what started as visible light became infrared radiation. Think of it like drawing waves on a rubber band. Now pull the rubber band. The waves stretch. They get longer, more spread out. That's exactly what the expanding universe does to ancient light. This is called redshift. The further away something is, the more its light is redshifted, the more it slides from visible into infrared. And Hubble in infrared was basically blind. It could see blurry smudges where entire galaxies were hiding. It could sense that something was there, but couldn't tell you what. And then there's another problem: the atmosphere. Even the best ground-based telescopes, even the ones sitting on top of mountains in the driest deserts on Earth, they're all looking through a layer of air that absorbs infrared light. Water vapor, CO2. It all acts like a filter, blocking the signal before it reaches any mirror. To see in infrared, you have to get above the atmosphere entirely. And that's exactly what James Webb was designed to do. Every single component of Webb was built around one obsession: capturing infrared light. Its mirrors, its sensors, its detectors, all of it optimized for the ancient, stretched, red-shifted light of the early universe. If Hubble was a human eye, Webb is the eye of a hawk. Same basic concept, incomparably more powerful. But building an infrared telescope in space is a genuine engineering nightmare. Problem 1: heat. Infrared is thermal radiation. Everything warm emits it: your body, your coffee, a telescope floating in space. If Webb operated at room temperature, it would be blinded by its own heat, like trying to photograph stars with a flashlight permanently taped to your lens. So engineers had to cool it down, way down, to minus 233 degrees Celsius, just 40 degrees above absolute zero, the coldest temperature physically possible. To achieve that, they built a 5-layer sunshield out of a material called Kapton, each layer as thin as a human hair, coated in aluminum, stretched across an area the size of a tennis court. One side faces the sun. Temperatures reach plus 85 degrees Celsius. The other side, where the mirror lives, minus 233. A temperature difference of over 300 degrees across a single structure. And that structure had to be folded up, origami style, to fit inside a rocket, then unfold flawlessly in the vacuum of space. No second chances. Each layer had to tension with millimetric precision, held in place by hundreds of cables and pulleys. If one layer snagged, if one cable jammed, and no shield, no cooling, no infrared, no James Webb. Problem 2: the mirror. Webb's primary mirror is 6.5 meters in diameter, far too large to fit inside any rocket as a single piece. So engineers cut it into 18 hexagonal segments made from beryllium, a metal chosen for its rigidity at cryogenic temperatures, coated in a layer of gold just 100 nanometers thick. 1,000 times thinner than a human hair, Gold because it's the best reflector of infrared light we know of. The total amount of gold used across all 18 segments? About the mass of a golf ball, that's it. But these 18 segments then had to unfold in space and align with each other to within a few millionths of a millimeter. A misalignment the thickness of a single virus would blur the image. Each segment is equipped with actuators capable of repositioning it to within 10 nanometers, 10 billionths of a meter. In the vacuum of space, 1.5 million kilometers from Earth. And here's the detail that keeps engineers up at night. Webb doesn't orbit Earth like Hubble. It sits at a gravitational balance point called L2, 1.5 million kilometers away. 4 times the distance from Earth to the Moon. At that distance, no shuttle can reach it. No astronaut can fix it. When Hubble developed a flaw in its mirror in 1990, NASA sent astronauts to repair it. 5 service missions over 20 years. With Webb, that option doesn't exist. If something breaks, it's over. $10 billion. 25 years of development. Engineers and scientists across 14 countries. And 344 single-point failure mechanisms. 344 individual components that, if just one of them failed, would destroy the entire mission. 344 ways to lose everything. December 25th, 2021. An Ariane 5 rocket lifted off from Kourou, French Guiana, with the James Webb Space Telescope folded inside it like an impossible piece of origami. Over the next 30 days, the world held its breath. The sunshield unfolded, layer by layer, exactly as planned. The mirror segments deployed and locked into position. The instruments powered on one by one. All 344 single-point failures held, every single one. And then, in July 2022, the first images arrived. The very first public image was a deep field of a galaxy cluster called SMACS 0723. A speck of sky, the size of a grain of sand held at arm's length. And packed into that grain of sand were thousands of galaxies. Some of them warped, stretched into glowing arcs by the gravity of the cluster bending space-time like a lens. This is called gravitational lensing. The gravity of massive objects curves space, and curved space bends light, acting like a cosmic magnifying glass. Through that magnifying glass, Webb revealed galaxies nobody had ever seen. Galaxies whose light had been traveling for 13 billion years before landing on that golden mirror. In a single image, we had looked further back in time than all of recorded human history combined. But that was just the beginning, because what Webb found when it looked even deeper, that's where everything started to unravel. To understand why scientists were shocked, you first need to understand what they expected to find. For decades, we had a model, the Lambda CDM model, the standard model of cosmology. And it told a very specific story about how the universe evolved. Big Bang. An unimaginably hot, dense state. For the first few 100,000 years, the universe is opaque, light-trapped, bouncing around in a plasma soup. Then the universe cools enough for atoms to form, light is released, and the oldest radiation we can detect is born. The cosmic microwave background, emitted about 380,000 years after the Big Bang. After that, darkness. Hundreds of millions of years of it. No stars, no galaxies, just hydrogen and helium drifting in the void. This era is literally called the Cosmic Dark Ages. Then slowly, gravity does its work. Gas clumps together, collapses under its own weight, and the first stars ignite. These first stars are enormous, hundreds of times the mass of our sun, and they burn fast. Millions of years, where our sun will last 10 billion. Around these first stars, the first galaxies begin to form. Small, chaotic, irregular, just loose clusters of gas and young stars without real structure. And over billions of years, these small proto-galaxies merge together, grow, develop spiral arms, central bulges, organized disk structures. Big, mature galaxies like the Milky Way are the product of billions of years of collisions, mergers, and gradual accumulation. This process, small things forming first, then slowly building into larger structures, is called hierarchical structure formation. It was the foundation of our best model of the universe. It worked beautifully. Measurements of the cosmic microwave background matched predictions. Computer simulations reproduced the large-scale structure of the cosmos. Hubble had seen distant galaxies as expected, faint, fuzzy, and small. Everything checked out. And then, Webb opened its eyes. Where Hubble saw blurry smudges, Webb saw galaxies. Real, fully formed galaxies, with spiral arms, disk structures, organized, mature architecture. Galaxies that looked like the ones we see nearby in the modern universe. Except they weren't nearby. They existed just 300 to 700 million years after the Big Bang. Think about what that means. It's like finding a 3-year-old child with a PhD in theoretical physics. It doesn't compute. According to everything we understood about galaxy formation, these structures shouldn't exist. The universe hadn't had nearly enough time to build them, and this wasn't one or two anomalous galaxies. In August 2025, a team from the University of Missouri catalogued 300 abnormal primordial galaxies in Webb's data. 300, some of them containing as many stars as the Milky Way. At an age when they should have been nothing more than chaotic clumps of gas and dust. Even their chemistry was wrong. Their metallicity, the abundance of elements heavier than hydrogen and helium, was 4 times lower than expected. These stars formed from nearly pristine primordial gas, barely enriched by previous stellar generations, which makes no sense, because at that point in cosmic history, there barely were previous stellar generations. Then, in 2023, a team identified a barred spiral galaxy. A galaxy with a central bar-shaped structure, just 2 billion years after the Big Bang. Bars are a sign of dynamical maturity. They take time to develop. They require the galaxy to have already settled into a stable, organized system. At 2 billion years, that was already jaw-dropping. But in January 2026, Webb shattered its own record. A galaxy designated MOM-Z14, the most distant galaxy ever detected. A redshift of 14.44, meaning we see it as it was just 280 million years after the Big Bang. And it is remarkably luminous for its age, already packed with a massive population of stars at a time when, according to our models, the very first stars were only just beginning to switch on. Here's the specific physics problem. In our models, gas converts into stars at roughly 10% efficiency. Out of all the gas available in a given region, only about 10% ends up as stars. The rest is dispersed, blown away by stellar winds, supernova shockwaves, radiation pressure. That's the upper limit we've ever observed everywhere we've looked throughout the modern universe. To explain some of the galaxies Webb has found, you'd need a conversion efficiency of nearly 100%. Every atom of gas becoming a star. 0 waste, 0 dispersal, 0 delay. We know of no physical mechanism that can do that. None. And then there are the little red dots. That's actually what astronomers call them. Not a metaphor, a working designation. Because when Webb started returning data from the early universe, scattered throughout the images were these tiny, incredibly compact, intensely red objects that nobody had ever seen before. Hubble never detected them. Its 2.4-meter mirror simply didn't collect enough light. Webb revealed hundreds of them, and nobody knows exactly what they are. They're too bright, too compact, too red, too early for any of our existing explanations to cleanly fit. There are two main possibilities, and both of them are deeply unsettling. Option A, they contain an impossibly dense concentration of stars for their era. Stellar populations so tightly packed into such a small volume that they exceed what our models say is physically achievable. Option B, they each harbour a supermassive black hole at their centre. A black hole with a mass exceeding 1 million times that of our Sun, one that simply shouldn't exist yet. Because here's what we thought we knew about supermassive black holes. A massive star dies, collapses, and forms a small black hole. That black hole slowly merges with others, gradually accretes surrounding matter, and grows over billions of years. It's an incremental process. Patient, long. But Webb keeps finding black holes that are already supermassive just hundreds of millions of years after the Big Bang. They haven't had anywhere near enough time to grow by the classical pathway. It's like finding a 100-year-old oak tree in a garden that was planted last Tuesday. In 2026, researchers proposed an explanation: direct collapse black holes. The idea is that in the extreme conditions of the early universe, when gas was still incredibly hot and dense, and before enough heavy elements existed to fragment collapsing clouds into individual stars, enormous gas clouds could bypass the star formation process entirely and collapse directly into a black hole. One step, no star, just gas cloud in, black hole out. It's theoretically possible, it fits the known physics of that era, but it remains a hypothesis, not a confirmed mechanism. And then there's the strangest idea of all. In 2007, a concept was proposed: dark stars. Not metaphorically dark, not black holes, something else entirely. The idea is that in the very early universe, before conventional nuclear fusion could power stellar interiors, collapsing clouds of primordial gas could have trapped dark matter particles inside them. And dark matter particles, under the right theoretical conditions, annihilate each other when they collide, releasing enormous amounts of energy. The result would be stellar objects unlike anything that exists today. Objects the size of a solar system, powered not by fusion, but by dark matter annihilation. Extraordinarily luminous, intensely red, which matches almost perfectly the observed profile of the little red dots. And at the end of their lives, dark stars would collapse directly into supermassive black holes, solving two problems simultaneously: the impossible early galaxies and the too early, too massive black holes. 4 objects in Webb's current dataset are consistent with the dark star model, but the model depends on the existence of a specific type of dark matter particle: WIMPs, weakly interacting massive particles that have never been directly detected. Until WIMPs are confirmed, dark stars remain what they are: a fascinating, theoretically coherent, completely unproven hypothesis. Science is honest like that. Then there's QSO1, an object discovered in Webb's data. We see it as it was 700 million years after the Big Bang, a black hole with 50 million solar masses, already enormous for its age, but that's not what shocked researchers. It's what surrounds it, or rather, what doesn't. Almost no heavy elements, almost no stars, just a massive black hole, essentially naked, floating in a near-empty environment. That shouldn't be possible under any classical scenario. Normally, a black hole this massive forms at the center of a galaxy. After billions of stars have lived and died, seeding the surrounding space with heavy elements. The black hole comes after the stars. But here, the black hole is there first. And there's almost nothing around it. An engine with no car, no wheels, no road. The hypothesis that emerged points back to an idea proposed by Stephen Hawking and Bernard Carr in the 1970s. Primordial black holes. The concept is that in the extreme density of the universe's first seconds, local collapses in the primordial plasma could have spontaneously produced black holes. Before any stars, before any galaxies, before anything else existed. Some would have been tiny, quantum scale, and evaporated almost instantly through Hawking radiation. But others could have been massive, up to 1 million solar masses. They survived, merged, accreted, grew, and potentially served as the seeds around which the first galaxies eventually formed. Not galaxies first, then black holes. Black holes first, then galaxies. The exact opposite of what we thought. We only have one confirmed candidate right now. And in science, one case proves nothing, but it's a thread worth pulling. In March 2025, a French-Chinese space observatory detected a gamma-ray burst, a flash of ultra-high energy photons that accompanies the most violent events in the cosmos. Observatories worldwide pivoted toward the source. The Very Large Telescope estimated the distance. The event had occurred 730 million years after the Big Bang. A supernova, the explosive death of a massive star, the oldest ever detected. Researchers then did something clever. They calculated when the supernova's light would peak, as observed from Earth, accounting for the redshift, which doesn't just stretch wavelengths, it stretches time. An explosion that lasted weeks at the source appears to us as unfolding over months because the expansion of space dilates the signal itself. They pointed Webb at the right coordinates, at the calculated right moment, 3.5 months after the gamma-ray burst. And they saw it, the light of a single star's death. Light that had been traveling for over 13 billion years through an expanding universe, caught by a golden mirror floating 1 million kilometers from Earth. Take a moment to actually picture that, because it's not a metaphor either. And what did this ancient explosion tell us? This supernova was almost identical to supernova we observe in the modern universe. Same luminosity profile, same spectral signature, same timeline of evolution. Massive stars from the early universe were already dying in essentially the same way they die today. More evidence that the universe reached structural maturity far faster than our models predicted. Not just at the scale of galaxies, not just at the scale of black holes, down to the level of individual stars. Here's something that doesn't get nearly enough attention. Webb isn't only staring at the edge of the universe. It's also examining things much closer to home, and in doing so, it's quietly performing something that would have seemed like pure science fiction 20 years ago. When a planet passes in front of its star, a tiny fraction of the star's light filters through the planet's atmosphere. And as it does, different molecules absorb different wavelengths. By analyzing which wavelengths are missing, you can determine what's in that atmosphere. It's like holding a glass of wine up to sunlight. The color tells you something about what's inside. Webb does the exact same thing, but with planets hundreds of light years away. Webb has already detected CO2 in the atmosphere of WASP 39b. It found methane and CO2 in the atmosphere of K 218b, a planet sitting in the habitable zone of its star. Not all findings are fully confirmed yet, but the fact that we now have an instrument capable of identifying molecules in the atmosphere of a world 120 light-years away, that's not incremental progress. That's a category shift in what's possible. So what does all of this actually mean? Are our models wrong? Not entirely, but they're definitely incomplete. and that is now certain. 3 explanations are on the table. The first, galaxies formed far faster than we assumed. In the extreme conditions of the early universe, gas may have converted into stars with efficiencies we've never observed. Mechanisms we haven't identified yet may have dramatically accelerated the process. If true, the core framework survives, but needs serious revision. The second, these early galaxies only appear as massive as they seem. Hyperactive central black holes, quasars, could be flooding their host galaxies with so much light that they look far larger and brighter than they really are. Like a 1,000-watt bulb making a small room look enormous. The third is the most radical. Some researchers have proposed that the universe could be much older than we think. Not 13.8 billion years, but perhaps 26 or 27 billion. That extra time would allow everything Webb has found to form naturally. But this hypothesis introduces so many other contradictions that it remains far outside the mainstream. And then there's the Hubble tension. A stubborn, persistent disagreement between 2 independent methods of measuring how fast the universe is expanding. When you measure it from nearby observations, you get one number. When you measure it from the cosmic microwave background, you get a different number. The gap is too large to be a measurement error. Some think Webb will help resolve it, others think it may make it worse. For now, no one knows. And this is exactly what makes science extraordinary. The cosmic microwave background was discovered by accident, by 2 engineers trying to eliminate background noise from a radio antenna. The expansion of the universe was discovered because Hubble's data refused to fit a static cosmos. The greatest discoveries in the history of science don't arrive when everything confirms the model. They arrive precisely in these moments of fracture, when observation and theory stop agreeing, when researchers stare at data that simply shouldn't be there. We built a time machine. We pointed it at the beginning of everything. And what we expected to find was a simple, primitive, infant universe, raw and unformed and quiet. What we found instead was a universe that was already complex, already structured, already strange. At an age when it had no right to be any of those things. Every answer Webb gives us opens 10 new questions. Every image pushes the boundary of what we know a little further and makes the ocean of what we don't know a little larger. We built the most powerful eye in human history. And what it's showing us is that the universe has been keeping secrets for a very, very long time. If this video changed the way you see the night sky, wait until you understand what it actually takes to survive out there. Click the video on your screen to discover the terrifying truth about why humans can't survive deep space. I'll see you there.